Today we're going to talk about thin layer chromatography. I'll show you how to set that up. Before we do, I'll do a little wrap on what is chromatography. Thin layer chromatography is one form of solid liquid chromatography. It's used for the rapid separation of very small amounts of organic materials. It can only be used to separate organic materials that have boiling points above about 150 degrees. So these are relatively non-volatile materials, and in our case today, we'll be separating colored pigments coming out of a plant leaf. The technique of chromatography is based on the principle that components in a mixture will distribute unequally between two immiscible phases. And this is the basis for liquid-liquid solvent extraction, which is another separation technique that we will do on a small scale for the first time in this experiment today. So thin layer chromatography is a form of solid liquid chromatography. The liquid that we use in thin layer chromatography is called the mobile phase, and then we have a solid support, which is called the stationary phase. In our case today, the solid support is silica gel, which is a polar material. At this point, you should be looking at a figure that illustrates what happens in what we call normal phase chromatography. And that's where there's a stationary phase, where the stationary phase is a polar solid, like silica gel, like we're using today. When a solution containing polar and a nonpolar compound come in contact with the TLC plate, the polar molecules are attracted to the polar support, while the nonpolar molecules remain in solution. When a nonpolar mobile phase is present, the nonpolar mobile phase passes over the plate and it leaves the polar compounds attracted to the polar support. So the molecules will, in the case of the TLC, the nonpolar compounds will move up the plate a little faster in this case than the polar compounds. At this point, you should be looking at another figure which illustrates the separation of a component mixture by normal phase chromatography. In this little figure, you're seeing three pigments that have been separated. What this shows is how we intend to do this experiment. We'll spot our leaf pigment on the bottom of a TLC plate, put it into what's called a developing chamber, which is a sophisticated name for a glass jar with a lid. And we'll put a little bit of solvent, the mobile phase, in the bottom of the jar, put the plate in the jar, screw the lid on, and in about 20 minutes or so, the liquid will move up the surface of the TLC plate by the force of capillary action. And as it does, it carries the pigments along with it. And depending on the polarity of the mobile phase will determine whether the polar materials move faster or the nonpolar materials. If you are careful today and you make the proper choice of mobile phase solvent, and the IVC stockroom has made up a really good mobile phase solvent to use. So if you use that solvent and you do this correctly, you may see as many as 7 pigments separate from the leaf. At this point now, I'm going to go over and show you how to actually set up for the experiment. All right, well now we're going to be working with chemicals, so goggles on. Our experiment said that we're going to use a spinach leaf, but we're too cheap to go buy spinach. What I found is a hibiscus leaf works really well, and hibiscus just happened to grow all around the outside of the IVC Chem building. So they're readily available to us, and I pulled a couple of leaves off this morning. And so here's what we're going to do. We're going to take one of these leaves and you're going to rip it into small pieces. And they go into this mortar. That ought to be enough. And we've got to put in some solvent now. We're going to grind these leaves essentially to a pulp in the presence of some solvent. And the solvent mixture has already been prepared by the stockroom. It's this mix of petroleum ether and ethanol. So they want us to start with 6 milliliters. So I'll get 6 milliliters. It doesn't have to be exact. Here's one of the reasons why. When we do the grinding, there's going to be a lot of friction generated, and the petroleum ether is very volatile and it's going to evaporate. So we're going to have to keep an eye on this and make sure that we still have some liquid in here as we continue to grind. It's common that you're going to probably have to add more liquid. All right, so now I'm going to lean on this thing and grind it with a considerable amount of force. So ladies, you're going to have to push. You're going to have to push down. Now I'll show you in a minute what the result is, but let me work this for a minute. You'll see when you're doing this that you're producing a very pretty green solution, and that's the whole idea. We're pulverizing the pigments right out of these leaves, and the colored pigments happen to be soluble in PET ether, which is not an ether at all in organic terms. That's just a common name for a mixture of hydrocarbons. And so these are just alkanes. So it's nonpolar alkanes mixed in with some rather polar ethanol. So we've got a mix of polar and nonpolar, and between the two of them, they'll dissolve most of these pigments in the leaf. All right, so I'm working up a sweat here, and I think I've got this pretty pulverized. So I hope you can see that I have a dark green, a very pretty dark green solution, and a bunch of leaf pulp. So then the next step of this reaction or this process is to try to remove the liquid and leave the pulp behind, and that's easier said than done, but we'll use a Pasteur pipette. And I'm going to try to remove the liquid and leave as much of the pulp as I can behind. I'm going to put the liquid in the test tube. The more liquid you remove, the harder it is to get the last bit. But I do want to try to get a lot of liquid, because in our next step, we're going to suffer some losses. So I'm kind of getting to the point of diminishing returns. So I've got not quite an inch of liquid, and you can see I've got some pulp in the bottom too. What we're going to do now is a liquid extraction. So I'm going to extract this ethanol petroleum ether mixture with water. So I've got my squeeze bottle with some DI water. What we're going to do now is this liquid solvent extraction, and this will be a little unusual compared to the other ones that we'll do later in the semester, in that we're going to do this one very gently. I'm going to add an approximately equal volume of water to the tube. All right, so what you may notice now is we form two layers. The reason is petroleum ether is a hydrocarbon, it's nonpolar, and water is polar, so they don't mix. So it's essentially oil and water, like that. Well, we do want to mix these to some extent, but if we shake it up like we would normally do in a solvent extraction, we're going to end up with an emulsion, and we'll never be able to separate these. So the recommendation is that we swirl the tube gently, and so this is very atypical, but that's how we'll handle this one. Now, one of the things that this solvent extraction accomplishes is it will remove the ethanol. The ethanol will be miscible with water, so the ethanol will go into the water, and what will be left behind when we're done will be our organic pigments in the hydrocarbon phase. So we've accomplished this, the first extraction by swirling that for a minute. And now I'm going to remove the aqueous layer. The aqueous layer is the bottom layer. So I go in with the pipette, and I'm going to suck out the aqueous layer, put that in there for waste. We don't want the aqueous layer. All right, so we have the organic layer at an equal volume of water. We do the same thing again. We do this 3 times. One more. All right, I'm going to give that a couple of seconds to separate. You notice that this time the aqueous layer is colorless, pretty much. All right, now I removed most of the water. Let's try that one more time. Here we go. There we go. Now, we don't have all of the PET ether layer left. You know, I told you we would suffer some losses. Part of that was because part of that organic mix was ethanol, and it went into the water. So we lost the ethanol. And there are also some losses when I pipetted out the water. But I need you to have, or you need to have when you do this, you need to have 3/4 of an inch or so, because you're going to suffer losses. And we're not done handling this stuff yet. Now I'm just going to pipette this stuff into this, our smallest Erlenmeyer flask, which is this little, I think that's our smallest. That's the smallest. Here we go, into the Erlenmeyer. And now at this point, we're going to dry this organic material with anhydrous sodium sulfate crystals. All right, well now we're going to dry this petroleum ether solution by using a little anhydrous sodium sulfate. And this is a crystalline drying agent, and because we're doing such a small amount, we shouldn't need a whole lot of sodium sulfate. So we put this in, and then you swirl it around. And the neat thing about sodium sulfate is when it does its job, it clumps up. It goes in as this powder. You can see that's a nice powder like salt grains. And when it, I don't know how well you can see that, but it clumps in the bottom. Maybe I want to add a little bit more so that when I swirl it around, I can see these little individual salt crystals in solution. Or in other words, I want to have some that is not clumped up. There should be some powder in there. As long as everything's clumping up, it's doing its job, and I want to add a little extra. And this would be very hard for you to see, but there are some individual grains up here on the bottom of the flask, and so I think I've added enough. Sodium sulfate will take the water out, and then once the solution is dry, we'll be able to spot it onto our chromatography plate and begin the experiment. All right, now we're going to prepare the TLC plate. So they'll come in a jar like this, and it's a piece of plastic that is coated on one side. So you'll notice that one side is very smooth and the other side is rough. But you have to be very careful with the rough side. That's the working side, because you can see on this one, for instance, that it's already chipped on the edge. These things are fragile, so you have to kind of treat them delicately, otherwise this silica gel will chip right off. What we're going to do, take a ruler and a pencil. Now make sure you use a pencil and not an ink pen, because the ink has organic colored pigment and it'll chromatograph if you make an ink line. So don't use ink, got to use a pencil. We're going to make a line 1 centimeter from the bottom of the plate.
Okay, stand by 1 second. Okay, stand by. Wait. Don't go yet. Wait.
So I'm going to draw a line, pencil line, 1 centimeter from the bottom of the plate. And then I'm going to make my little target spot right in the middle of that plate, or right in the middle of the line in the middle of the plate. That's the target that I'm going to hit when I spot the colored solution onto the plate. To do the spotting, we use an open end, or both ends open, capillary tube. So these are not the ones that we use for doing a melting point determination where they have one end sealed. These capillaries, make sure you're using the right capillary, open at both ends. Now, it's been 10 minutes since we did this. This solution should be dry. I put the capillary into the solution, and you notice that the solution, can you see it wicks up? It wicks up into that is capillary action. And that same phenomena will be what moves the liquid up the plate. The liquid will wick up the plate just like the liquid rose into this capillary. Now, what I'm going to do is I'm going to lower this right onto that target spot, but I want to do it quickly because I want to make as small a spot as possible. So I'm going to go bing, not bing. If it goes bing, it spreads out and I get a really wide spot. That's no good. So quickly. Now, I'm going to wave that around for a minute and let that first spot evaporate. The petroleum ether is very volatile, so it shouldn't take it long to evaporate. I'm going to get a little more in the tube, and I'm going to do it a second time, right on top of the first spot. Again, very quick spot. I think you can see now a couple of times, and I've got a pretty good dark green spot. If I go for darker and spot it some more, the spot's going to get larger and larger. So I kind of reach a point of diminishing returns. I might want to do one more just to make sure I have plenty of material. The reason is the darker that spot, the easier and the more pigments I'm going to see. The easier it'll be to see the pigments. Some of them are fairly light colored. All right, now that is a really dark spot. So we're going to let that dry. Here is our what's called the developing chamber, which to a non-chemist this would look like a jar and a lid, but to a chemist this is a developing chamber. You've got to put the right solution in there for this experiment, and the one that really works the best is this mixture that the stockroom has been kind enough to make for us. It's 3 parts PET ether and 1 part acetone. So the PET ether is very nonpolar, the acetone is very polar. So it's a mixture of polar and nonpolar, and it turns out it does a great job separating these pigments. So what I want to do is pour a little bit into this jar, and the intent is I want not quite a centimeter, because this line is at a centimeter. I don't want the liquid level above the level of the line. When I put that plate in, the liquid can't go above the level of the line, otherwise this is a solvent. It dissolves the pigment right off of the plate and into the solution, and the experiment's over. So the only way this is going to work, put in a small layer, less than a centimeter in depth. And now we have to try to lower this plate in here without splashing. So I'm going to turn that around so the label's not in the way. And try to lower this without splashing. And this is, again, this is easier said than done. Okay, so if you can see right now, the liquid has not reached the line, but it's wicking fast. Now we put the lid on, and at this point, don't move the jar. Just let the jar sit stationary. We don't want agitation because it'll create waves, and then that'll destroy what's called the chromatographic front. This liquid should be wicking evenly up the plate. In other words, left side and right side moving together. If you jostle the jar and you create waves, then one side will be going higher than the other, and the separation's not as nice. I don't know how well you can see this on the camera, but I can look in there and already I can see my green spot, the major green spot has moved off of the target. It's moved up about 3 or 4 millimeters. Above it is a darker spot, smaller but darker, and above that, almost right there where the solvent front is a bright yellow spot. So already we're getting separation. Now the wicking process is very rapid at first, and unfortunately it kind of slows down. So it's going to take maybe 10 minutes for the solvent to wick close to the top of the plate. So at this point, you just kind of sit and watch, but please keep your attention on this, or don't be too inattentive, because you have to stop it. You have to stop the experiment before the liquid reaches the top of the plate. I think you can see on the camera that the liquid, as it wicks up, has darkened the plate where it's wet. And so we'll stop this when the wetness, or that darkened area, is about 1 centimeter from the top of the plate. And at that point, we'll remove the plate and draw a pencil line where the top of that solvent front is. And that we need that distance, the distance from the target line that I drew with pencil to the line that we're going to draw with pencil, we're marking the solvent front. We'll need that distance in order to calculate what's called the RF values, and I'm not going to talk about that in this video, because this is just to show you the technique, but that'll be part of the experiment, will be to calculate what's called RF values for these various spots. And the reason you want to draw the line as soon as you remove this from the solution while it's still wet is because most of this is petroleum ether, and acetone's very volatile also. So when we take it out, it's going to dry in the air very rapidly, and if you don't mark the solvent front right away, you'll not remember, or you'll not be able to see where it was. Also, we're going to want to circle the spots right away, because especially some of the light yellow ones will disappear within a couple of minutes. So we need to mark the spots with the pencil right away. I think for the purpose of this video, I'm going to stop this now. It's about 1 inch from the top, but in the interest of time, we'll just stop it now. You would let that solvent front rise a little higher before you stop yours. All right, we'll zoom in on this in a minute, but let me mark the solvent front. There's the solvent front, and very quickly I want to mark the spots. All right, now I hope you can see this when they zoom in. The colors are still fresh, but there's no color left here at the target line. It looks like everything moved off at the target line. There's a yellow spot here, which I've circled with the pencil, a light green spot, a darker green spot, a kind of a gray spot, and a yellow spot. So we got 1, 2, 3, 4. We got 5 pigments in this short experiment. I think perhaps if we'd let the solvent front go up, some of these dots might have separated into even more spots. But even in this quick and dirty experiment, we got 5 different colored pigments out of the hibiscus leaf. Presumably, one of those green ones is chlorophyll. I don't know what the other ones are. But this is a technique that organic chemists use to separate very small amounts of higher boiling organic compounds. All right, well, this concludes our experiment with thin layer chromatography. Good luck. I'll be walking around to see how you do.